Welcome, everyone. It's the night before the snowstorm, which may or may not happen. Last forecast was 3 inches. I don't know what we're going to get tomorrow, but welcome, everyone, especially the home audience and the live audience in the studio. I'm here to help you tonight. You're here. I want to help you. I'm honored Professor Miles is here also. And always, we have to thank Andrew. Andrew for giving up his time to be here to record this, and then he's going to process it and upload it for us. Andrew, thank you very, very much. Okay? All right. I want to get right to it. Now, one word of suggestion, if you have a question, ask it. Why? Because probably someone in the home audience has the same question and they can't answer it. So I want this to be worthwhile for you tonight. So ask whatever questions I can be of help on. The exams are posted on the course website along with solutions, pardon me. And I thought we would do the most recent exam. Okay, which is Quiz 1, Fall 2018. So this is posted. So my colleagues at home, I've opened up Quiz 1, Fall 2018, the solutions. Now, just to give you the heads up, we're recording this on February 11th. We haven't yet in our lectures finished Chapter 3. So there's one or two topics that will be a little new for us tonight. So we'll go over it tonight, and you'll see it again Friday. Okay? So let's just dive right into this. All right. Okay, so this is a Chapter 2 problem. And let's see if I can figure it out and figure out what I got to do to solve it. We're given a sensor that can be modeled as a first-order system. So that means first-order differential equation. Now, the input to this sensor is a constant. And it is applied at t equals 0. You haven't missed anything. No, was there anyone else out there locked out?
No.
Okay, good. Thanks. So we apply a constant input at t equals 0, and this constant input has a value of 10. The initial reading of the sensor, that's the initial condition, is -5. Now, I'm asking you to determine the largest the time constant tau can be, given that the sensor must satisfy these two requirements. So I'm thinking, okay, what happens here? My colleagues, I have time, and I have the output of the sensor, and let's see if I have the numbers right. At t equals 0, it starts at -5. And as t goes to infinity, I see nodding of the head, so I know I'm doing okay. It goes up to 10. And because it's first order, I know it's an exponential rise like that. Now, what controls the rate of change here? Tau. Okay, tau is going to govern how quickly this sensor responds. So we want to pick a sensor whose value of tau makes these two requirements possible. The time for the output of the sensor to reach 90% of its final value should be less than a half a second. So we're going to set that up, and we're going to solve for tau. And then the error at t equals 0.25 seconds, this will be less than or equal to 3. And the error is defined as the true value of what we're measuring minus the output of the sensor. Now, determine the maximum value of tau which will satisfy the above two requirements. So here's what we need to do. We need to solve the problem Magdalena twice. Okay. And we're going to get two values of tau, and then we'll figure out which one to pick. So I say, okay, let's do it. So the first one, for the first requirement, the time to reach 90% of the final value, less than or equal to half a second. All right, so now my colleagues, I hope you're comfortable with this. And if not, I need feedback. I need to help you. Here's the sensor. Input is x of t, output is y of t. Now, this you have to know from first order. Y of t, the output, is ke to the minus t over tau, plus the constant input. Because if it's a constant input, we're going to eventually get there. So this equation, I need you to know for the exam. Ke to the minus t over tau plus the input, which becomes the final value. Okay? Now, how do we solve for k? I think you all know this. We solve for the initial condition. We use the initial condition, pardon me, to solve for k. So at t equals 0, y is minus 5. So I set minus 5 equal to ke to the minus t over tau, where t is evaluated at 0, plus 10. And what I get is ke to the 0. Why e to the 0? Because t is 0. All right. So I get ke to the 0 plus 10. K is minus 15. So notice the first thing we had to do was to get the equation for this system. And it all started by knowing it was first order with a constant input. Let me pause. That's the first part of the problem. How am I doing? All right. So what we now do is say, all right, we now have the key first step in the problem. We know the equation for the output y of t. So I'm now going to have to solve this system twice. First requirement, the final value is 10. Do you see that? As I tried to graph over here, the final value is the constant input. So the first requirement says 90% of the final value.
Yeah, I was wondering, because the sensor initially had a value of minus 5. If the true value is 10, how come the value doesn't go up to just 5 because of systematic error?
That's an excellent point that I never thought of. That is actually very insightful of you. I don't think it makes a difference in this sense because I was not assuming a systematic error. Help me out. You raise a great point. You're saying if we start out at minus 5, doesn't that cause a systematic error? Not necessarily. Think of a thermometer that starts out at room temperature 68 degrees and we put it into boiling water. It's going to get to 212. So the initial condition not being 0 doesn't necessarily mean that it's biased. You know, this could be measuring background radiation. So background radiation is 5, just from whatever the units are from everything that's around us. Now we turn a machine on, and the background radiation goes to 10. We're going to approach 10, like we did with the thermometer in the class. How did I do? Did that help? All right, so we approach the final value. As we did with the thermometer. Maybe the thermometer is a better example than the background radiation that I was giving, but the thermometer went from whatever the temperature was at room temperature to the high temperature of that water that was on the hot plate. My background energy example might not be good because you still have that energy, but the final value is 10 and we approach it here. Did I do okay? Thank you. That was a very insightful question. Did I do all right, my colleagues? All right. So we approach 10, but I want to find out 90% of the final value, so it's 0.9 times 10. Now, what do I know? I know t is 0.5. Where did I get that? That's part of the problem statement. I want to find out what's the largest I can make tau and still get to 90% of the final value in 0.5 seconds. So I solve now for t. Okay, so my colleagues, I encourage you to go through this. Nothing fancy here. Just bring this over, subtract it, and now I have to solve for tau. I have t. I hope I didn't say we have to solve for t. We're solving for tau. And I'm going to now take the natural log on the next page. Andrew, how am I doing so far? Good? All right. So I go to the next page, and I take the natural log, and I solve for tau, and I get approximately 0.185 seconds. So that means if I have a first order sensor with that value of tau, I will reach 90% of my final value in half a second. Okay. First part of the problem is done. To my colleague who we locked out, how we doing, my colleague? We're doing good? All right, good, good. All right. All right. So that's the first half of the problem. Now, the second half of the problem, let me just read it again. Second half of the problem said, okay, at a quarter of a second, t equal 0.25 seconds, we want the error to be less than or equal to 3. And I say, great, how do I define the error? It's the true value minus the output of the sensor. Now, if I could just go to this graph for just a second. Suppose this is, I'm using 0.25. This is 0.25 seconds. Okay? The sensor is reading this. But the real value of what I'm trying to measure is this. So this here is the error. And that's what I wrote here. See, the error is the true value of what I'm trying to read, which is 10, minus the value of the sensor at that moment. And the fact that they're different, that's the error. So I say, okay, can I solve it? I think we should be able to solve it from just the first order equation. So I come down here. Now, please stop me if this doesn't make sense. The error is defined, I gave you this, as the true value minus the value of the sensor. So the true value I'm trying to measure is 10, minus the actual value of the sensor, which is k e to the minus t over tau plus 10. But we solved for k before this, minus 15. E to the minus t over tau plus 10. So notice 10 minus 10, and I have minus a minus. This converts to 15 e to the minus t over tau. Okay. Now, what do we require? This is the error. I want the error to be less than or equal to 3. At what time period? 0.25. Solve for tau. So I solve for tau. Let me slide down a bit more. Okay. So now, my colleagues, it's interesting to note what happens to the sign here. You do get a positive value. It might seem unnerving when you first solve it. You have a negative here as you solve all of this, and it's less than or equal to tau times this quantity. You might say, gee, how am I going to get tau positive? As you look here, there's the answer. We're getting natural log of a number less than 1. So this is a negative number. And of course, we have the negative number here from the math. So tau is going to be positive. Good. Please.
Because the ln of 3 over 15 is negative, that's why you flip the sign.
Very good. I hadn't even thought of mentioning that. You're absolutely right. Since we now divide by a negative number, we flip the sign. Thank you for the assist. That was a very nice observation. Thank you. Beautiful. So here I get a tau of 0.155. How are we doing? Great, thanks. Okay. So I look at this and say, great. Now, does this statement make sense? To me, this is the most important part of the problem. You have now solved the problem twice. You got two values of tau. And we need to satisfy both requirements. I picked the smaller of the two taus. How long does it take to reach the final value? Approximately 5 tau. So the smaller tau, the quicker I respond. So if I pick the larger tau, that would not satisfy the other requirement. So I need to be aware that I have to pick the smaller tau to satisfy both. So in this case, I picked tau, the smaller one, which was the second one we solved for, 0.155 seconds. Problem 1, Chapter 2, First Order Systems. How do we do? Okay. Home audience? All right. Okay. All right, good. All right. Now, all right. This looks like a filter problem. Okay. So we're getting into a filter problem here. And Butterworth, oh, we discussed that on Friday, our last exciting lecture together. And we discussed Butterworth, and we say, okay, maximally flat, remember? Maximally flat Butterworth, got it. All right, we're going to examine two important design parameters, the corner frequency and the order of the filter. I love this problem. That's me. I think this is a fun problem. Okay. The input signal to this low-pass filter has a frequency of 750 hertz. So I drew this up here as part of my solutions, 750 hertz. I'm going to call that the good signal. Okay? Then there's a bad signal. That's the noise. The noise is 1,000 hertz. So you see what I'm trying to do? I want the good signal to go through, and I want the noise gone. So I want a low-pass filter. All right. Here. The design requirement of this filter is that the voltage gain of the filter at the noise frequency. Let me say that again. The gain of the filter at the noise frequency is meant to be equal to or less than minus 34 dB. Now, a negative number means the gain is less than 1. All right, so this is a tiny number we're getting out, which is good. I want the noise to go away. Using a corner frequency of 825. Now, what does that mean? Below 825, you're through. Above 825, I mean, you get through. Below 825, you get through. Above 825, we start dropping off. So I tell you, the corner frequency is 825. Determine the order of the filter. Now, we went over this towards the exact end of our lecture on Friday. So you may not have time to really absorb this yet, but now you're going to see it. There's one equation you need to satisfy part A. I give you this equation. I give you this equation on the formula sheet. You might remember I wrote it on the board, but now you're seeing it again. The gain for a Butterworth filter as a function of frequency is 1 over the square root of 1 plus f over f sub c. And that quantity, f over f sub c, is raised to the 2n power. And my colleague n is the order of the filter. Perfect. Now, please make a note. This gain has to be a non-dB. So I already threw you a trick, a curve. I said we want the gain to be minus 34, but that's minus 34 dB. So again, this formula is given on the formula sheet. Just make sure you can do it. We have to convert this to non-dB. So minus 34 equals, and this is the formula for voltage gain in decibels, 20 log to the base 10G. I solve for G, and it turns out I get a really nice number, right around 0.02. Now, what that means is I want to get only 2% of the noise out. That's great. We're getting rid of 98% of the noise. So I'm thinking, all right, what order filter do I need? Now, be careful. I'm looking for a gain of 0.02 at the noise frequency. So I want the gain at 1,000 hertz. That's the noise frequency. So I go 1 over square root of 1 plus, now 1,000 over 825. What's 825? The corner, or the break frequency. And that quantity is raised to the 2 times n. And here it is. I want this all to be less than or equal to 0.02. The only unknown I have is n. Now, all of this is posted. You can go through it. Make sure you can solve for n. So we go through it, solving step by step by step by step, and I get a value of 20, which is a big number, 20.73. Now, can I use 20? No. I always have to go up. Even if it was 20.1, I'd have to go up to 21. So it's not rounding. You always go up. So to make this system work, I need a filter whose order is 21. Sounds ambitious. Are we good? So I say, all right. I still some people taking notes. Doing okay? Good, good, all right. Now, let's think about this. It says here, oh, by the way, let me just now, I'm going over here. This is what I like about the problem, because it really got me to think, okay? Frequency, gain in dB, right? It's flat, and then it gets here to the corner frequency. That was what, thank you, 825. And where was the noise? 1,000. See, and we wanted the gain to be like minus 35, right? So it's even like it's really low, right? So we need to have a very sharp slope. You see that? It's very powerful markers here. Won't be able to drive home. Okay. Now, here's what's interesting. We are already down 3 dB at the 825 part. Now, what was the value of the good signal? That was 750. So here's the deal. How much of the good signal am I getting with a 21st order filter, and the break frequency or the corner frequency is 825. Now notice, be careful. This is easy, but it's very easy to trick yourself up. This is the gain at 750. So now I put 750, not 1,000. Same corner frequency, 825. And now I know n is 21. Look at this. I'm getting out 99% of the good signal. So I look at this and say, I've done it. I've got 99% of the good signal. I get out 2% of the bad signal. Life is great, except I got a 21st order filter. Now, I'm afraid if I give it to the intern to design, they might give it back to me. So I got to find a way to kind of balance this out. So this is good. I met both requirements. Everything's happy, or at least I think I've done well. 99% good, 2% bad. I think this is great. But wait. I am surprised that this may be an expensive low-pass filter design. I really should not have been surprised. Because what? The bad frequency starts at 1,000. Where's my corner? 820. I don't got much room to get down to 2%. I got to fall quick. How can I make a less expensive filter? What do I do with this? Bring it back. But what's going to happen? I'll get less of the good signal. Oh, engineering trade-offs. I love it. All right. So you say, look, let's make, forget the, was it minus 35 dB for the 34? Look, I'm willing to live with a little more noise. Let's go with minus 26 dB. Okay? And let's change the cutoff frequency to 800. Repeat the problem. Convert to non-dB. Remember, to use that formula, you need non-dB. So minus 26 dB gives us 0.05. So now I've gone from 2% of the noise to 5% of the noise. And I think I can live with that. So I go to 5%, and I'm also backing off on the cutoff frequency. So the cutoff frequency is going to get closer now to the good signal. I think the good signal was 750. So I'm a little bit above it. I'm at 800. So I'm hoping these two will give me a smaller value of n. I plug everything in. I get, again, be careful, it's the f that's here goes in the numerator. I want the gain at 1,000, and I have 800. And now I don't know what n is for this case. And I need that to be less than or equal to 0.05. I actually found this fun to do as I was doing it. So now I get 14. So, my colleague, did I scroll down too much? Were you?
No, you're fine.
We're good? Okay. So what I get is 13.42. Always go up. Don't round and say I can get by with 13. You always got to go up. So now I've gone from a 21 order filter to a 14 order filter. And now instead of getting 2% of the noise, I get 5% of the noise. So I say, all right, how much of the good signal do I get? I used to get 99%. Now I get 92%. How did I get that? What's the good signal? 750. Remember, what's here, you put in the numerator. What's the corner? 800. What's n? 14. So now I've gone to 92, 93% of the good signal with 5% noise, as opposed to 99% of the good signal and 2% noise. But the order of the filter has gone down from 21 to 14. I think this is pretty interesting. This is exactly how we would do filter design. You see, as I mentioned in lecture on Friday, if there were no trade-offs, I don't know if we would need engineers. You need someone to think like. See, I think this is a wonderful way to think. All right, I hope I don't get mad at me. We're going to do it one last time. Absolutely.
So I was going to ask, if you dropped it to like 775 or 750, how close would you get to that negative 3 dB?
Right. You're a man after my own heart. I couldn't leave this problem only doing it twice. Right? Because I was learning too. I said, this is interesting. I got to do it a third time. See, you and I, we're together on this. Okay? Now, how about we go to minus 20 dB? I'm really lowering my standards now. Okay? I went from minus 34, 2%, to minus 20. And it turns out that is 10% noise. So I went from 2% to 5%. I'm saying, the heck with it. 10% is good. All right? So I get that, and I say, okay, what's the order filter, right? I had 21 or 22, whatever it was. I went down to 14. Same thing. Now, just be careful. I'm saying this because we saw a few mistakes here. Whatever number goes here goes there. So you're figuring the gain at the noise frequency. Now, we solve for n. 8. Okay. Was it 21 or 22 the other one was? 21. So we went from 21 to 14 to 8. Okay. But the price I pay is I've gone from 2% to 5% to 10% noise. Right? Now, how much, here it comes, how much of the good signal? Now, notice, this gives us the magic number, 0.707. Because now, we're at the frequency that equals the cutoff. So it doesn't matter what power filter I have. This is 1. So I get 1 over the square root of 2, 0.707. That means I've lost almost 30% of the good signal. So now it's a choice of how much you want to spend, what you want to do in terms of meeting system performance. Can you live with this? Maybe not. So to me, this was fun to go through. Please.
Optimally, you would test out every frequency between that, so like anything between 750 and 1,000.
Right, well, we know the slope, so help me out. You're bringing up a very good point. In this scenario here, we have an 8th order filter. We know the Bode plot. We know that the slope is 6 dB per octave per order. This is 8th order. So, yeah, we could test out every frequency, but there's also equations that would give us the graph. And I thought the two most interesting points were how much of the good signal we get and versus how much of the noise. That's the trade-off. And the key parameter is N. Now, I have been grading and working on solutions. I think there is something about the engineer in us that absolutely hates these questions. This question says, discuss your results. Panic. You shouldn't panic. You're going to be fine. Okay? Answer the following questions. Why did the original design result in a very large value of N? To me, and I saw it in your face when I wrote it down, we didn't start the break until we were close to the noise, however you want to say that. Okay? If the noise is 1,000 and you don't start going downhill to 825, and you got to get down to 2%, you are on a steep decline. That's a large N. That's it. However you want to say it. Don't memorize this. This is my own words. Say it any way you wish, but just say it. You didn't have much room. What is the specific advantage of selecting f sub c to be 825 in the original design requirement? I got 99% of the good signal. The good signal was only up to 750. If I choose the corner to be 825, I get 99%. It says 0.9, but in the document, I'm sorry, it's slightly off kilter here. It's 99%. Almost equal to 1. Why did changing the requirement from C to D result in a reduction of the value of N? Okay, so why did changing the design requirements result in a reduction? It's because f sub c was moved further away from the noise, right? We started with f sub c, noise at 1,000, f sub c was 825, or was it 820? Then we backed it off, right? We pulled it close. So now you had more room to drop. Your slope doesn't have to be as much. I wrote it in my own words. Okay, so that's it. And what is the disadvantage of selecting f sub c equal to the corner? We only get roughly 71% of the good signal. Summarize your observations. I don't mean to drive you crazy. I just thought this was a great problem. You can read this on your own. I think from your body language, you all got this. Okay? Now, I want you to know, if I ask a question like this, I meet with the TAs. And I say, look, they're not going to get everything I write down word for word. I say, here's the key point. So we're looking for key points. Okay? So as you move the corner closer to the noise, you got less room to drop. It means a higher order filter. As you move the corner back towards the good signal, all right, I can get by with a lower order filter because I got more frequency to drop. But I'm now killing myself. I'm not getting as much of the good signal. That's it. That's everything I wrote. But that's so as long as you got it, do you think you're comfortable with it? Great. All right. Excellent. You've done filter design. That's some pretty heavy stuff. I love it. Okay. I'm up to problem 3. How we doing so far tonight? All right. So, problem 3. Oh, yeah. Okay. Professor Miles, I think if this is the problem I'm thinking it is, it became an algebraic nightmare. Okay. So we should learn from the errors of our youth. Okay. I wouldn't give a problem exactly like this again because it became an algebraic manipulation, which wasn't the intent. So I'm going to avoid the algebraic manipulation. I'm just going to set up the problem. Okay? Let's see if it makes sense the way we're going to discuss it. All right, a sensor has a Thevenin equivalent. Good. Do I have to determine it? No, you did that in circuits. So that's circuits. Okay? The sensor is connected to 2 resistors as shown below. And let's just take a peek. See? R1, R2. So from Friday's lecture, we know this is an attenuator. So we say, all right, the output of this attenuator is to be connected to a measuring instrument which has an input resistance Rn. So before I get to the second paragraph, I think I understand this. RT and VT, that's the sensor. The attenuator is R1 and R2. And Andrew, I think I'm going for loading error here, although I haven't mentioned it yet. So the loading error is V before minus V after. So this is before, and then we're going to connect R in and get the after. Now, you are given that the loading error due to the addition of Rn should be no more than P times V sub t. For example, if by the way, P is going to be generally a small fraction, so P could be 0.01. That was, I think, the homework problem, 1% loading error. So you want the loading error to be no more than P times V sub t. Except I don't tell you what P is. I want to solve it just generally solve it. Okay, 1%, 2% error, you would then change P. Determine the minimum value of Rn. So your loading error is P times V sub t. Turns out this is a beautiful problem because this is this is a common network configuration. So if you say, if Magdalena said, I want 3% error, and someone else said, no, I want 1%, we just got to plug in P of 0.03, P of 0.01, we're going to get it. So I actually thought this was another fun one. But determine the minimum value of Rn. Now, being the guy that I am, look at this. I thought I was giving you a break, and it wasn't that much of a break. To simplify the analysis, we can assume RT is small. That means it's 0. It's small compared to everything else. Thus, here it is. Now, I'm not going to worry about the algebra, okay? What I want to worry about is the front part of the problem. Can you set it up? Here's what I absolutely need you to know, and stop me if it doesn't click. Loading error is V before minus V after. Now, what that means is find V out before you add R in. And then repeat it after you add R in and take the difference. That's it. So, one step at a time. Now, I want to make sure I don't. Here. I want to try and show as much on the screen at once as I can. All right. V before. Now, please, I want you to get this right. That's V before we've added R in. This is voltage division. R2 over R1 plus 2, R1 plus R2 times V sub t. That's V before. Now, you might say, wait a minute, what happened to RT? Generally, RT is very small because you want RT to be small. So I think it's reasonable in many cases to neglect it. So RT is neglected. This is V before. Now, V after. I now add this. I'm hoping you see this. If not, please let me know. I have to get an REQ. I have to get an REQ somewhere here. I don't know if I wrote it down. I might have written it down. But REQ is product over the sum for two resistors. So REQ is R2 times Rin divided by R2 plus Rin. Now, what's V after? RQ, right? Not just R2 anymore. It's the two of them together. REQ. It's REQ over REQ plus R1. So, what do we have? Loading error is V before minus V after, and we want that to be some percentage P of V sub t. What's nice is that the V sub t's cancel, so that expression becomes this. Now, That's pretty much the essence of the problem. Do you have it? Are you okay with this? We're good. So now the challenge said we have to find a value of Rn. Now here's where it gets messy. Where's Rn? It's in REQ. So this is where the algebra got a little hairy. And basically, I solved for everything. I defined a constant. The answer turns out to be quite beautiful. My colleagues, tell you what, I won't ask you to do all this algebra. I'll ask you to do some, but I'll avoid this complexity. Okay, I'll leave it for you to read. There are other exams. Look at my spring exam from last year or the fall from 2017. You'll see a couple other loading problems. The key thing is knowing how to write the loading error. And what I did was you could then cancel the v sub t's in this problem and here. Now I had to solve for R2. And so I just did all the math. I mean, you can follow all of this. Became one of algebra. I had to define what x is. X got a little messy, and that's it. I'll be kinder with you.
Just throwing some values. A little bit easier rather than just all variables.
That is one way to ask this problem. One way to ask this problem is to give you numbers and say, you know, what should be the value of Rn or whatever I was asking there, Rn. So that, and I've done that on prior exams. And if you go back 1 or 2 or 3 semesters, you should see that. All right, how did we do?
How would we go about this if the Thevenin resistance was not 0?
Oh, if the Thevenin resistance was not 0, now that's something I might do if it's numbers, because that's just a simple addition. So let me answer your question directly. So suppose now I were to give you, let's say, well, I'm not saying I'm definitely giving you numbers, but that's a possibility. If I were to give you numbers, so this is no longer 0, what would change is V before would be R2 over R1 plus R2 plus RT times VT. And correspondingly, the V after, and I'm sorry, I know it's not showing up. There's a VT here. If you open up there's a VT here, right? Because this is voltage. This is just the ratio, you see? It might be, I might break it, but it's slightly off kilter. Please check the document. This is, now to answer your question, REQ over REQ plus R1 plus RT. And then there's a times VT. You'll see it in my PDF file. Times VT. That would be the difference, which is okay if I give you numbers, right? That won't be bad. We're good? 3 problems done and dusted. All right. All right. Okay, now you're getting a preview of Friday's lecture, okay? Turns out an op-amp can filter, which we know. It can amplify, which we know, but it can also integrate. Now, this you haven't seen, so I'm hitting you with something new. We'll go over it again Friday. So let me do this now. Suppose you have an op-amp integrator. So the op-amp integrates. You say, fine. Do I have to know anything? No, just this formula here, but it's on the formula sheet. This is the formula. So what's the formula? It says here that an op-amp can be an integrator. So V out of T equals minus 1 over RC. Professor, do I have to derive this? No, you don't have to derive it. 0 to T. And this is V in of a dummy variable for integration. I call it tau. It's not the time constant. Times d tau. Then plus V out at T equal 0. Now, you don't have to know this formula. This is given. So now, what's the input? I give you the input as 1/2 times t squared. And that's for 5 seconds. What's the output? I tell you that R times C is 1. And I tell you that the initial condition at the output is 0. So what I get, now please, feel free to ask me questions. I especially here, because this is your first time seeing it. I say, what's V out of T? So I say, well, what's the input? 1/2 t squared. Fine, plug that in for V in. And it goes from the minus, you see? Minus, I told you RC is 1, so it's minus, outside of 0 to t of 1/2 tau squared d tau. So I say, okay, I can integrate that. At least I think I can. I take the 1/2 out and I get this. The integral of tau squared, tau cubed over 3. And I say, I got it. And I say, excellent. And I get minus 1/6 tau cubed from 0 to t, which is minus 1/6 t cubed. How do we do? Now, I want to tell you the number one mistake more than one people make. I don't want you to make it or you out there. You see where I integrated from 0 to t? What some people do is to integrate from 0 to 5. That gives me the final value. That gives me the value at 5 seconds. I want to know the value at all time between 0 and 5. So keep it t in the upper bound. If you put in 5, you're only solving for 1 point, the last point. So my colleagues at home, keep the upper value of the integral, the bounds, t. Does that make sense, my colleagues? Okay, now, do you know why I'm asking this question? So right now, to me, this looks like a basic integral. I get minus 1/6 t cubed, but then I say, wait! The key question is, when does this equal minus 15? Why am I asking myself that question? Right. That's an excellent, excellent point. Welcome back. That's an excellent point. We are powering this op amp with plus 15 and minus 15. It can't have an output more positive than plus 15 and more negative than minus 15. That's the ceiling and the floor. So I say, okay, when does this equal minus 15? And what I get is it equals minus 15 around 4.48 seconds. Okay? So now, what happens? Does this make sense? This is a challenging problem, and you're hearing it before I gave the lecture material, so I expect questions. It's minus 1/6 over t cubed, so it starts integrating. Minus 1/6 t cubed, perfect. But at t equal to 4.48 seconds, this quantity becomes minus 15. And it stops. It says, that's it. Can't go any more negative than minus 15. And that occurs now at minus 15 from 4.48 seconds up to 5 seconds. How do we do? We're okay? Don't worry. I sense you feel bad you missed it. Don't worry. You'll get it on the. I know. You'll be fine. You'll be fine. I have total confidence. All right. Now, the wording of the problem, I say in your analysis, you can ignore any internal voltage loss. That means we're going with plus and minus 15, nothing less, not plus and minus 13, going with plus and minus 15. We're good. That's 4A. We're good? Okay, one more problem, which you haven't seen before. Here, before we even read the problem. Okay. An op-amp can compare two signals. Now, we haven't discussed this yet, but you will on Friday. We will. Oh, yes, Friday. So a comparator can be built using an op-amp. Now, here's the only thing you need to know. And you might say, well, why is this true? I'll show you that in the lecture Friday. But even if you forget why this is true, this is what I need you to know. A comparator has a positive input and a negative input. Now, how could you forget this? You can't. This is so basic. You're going to love it. If the positive is bigger than the negative, the output is 15 volts. If the positive is less than the negative, the output is minus 15. That's it. Can I share with you why? It's great. It's great. What's the gain of an op-amp with no external resistors? Infinity? I'll settle for 200,000. Suppose V negative is 5 volts. And suppose V positive is 5.01. What does the op-amp do? 5.01 minus 5, 0.01. 0.01 times 200,000? 15. 0.01 times 200,000 is 15. Because I can't get any more than 15 volts out. Likewise, if V positive was 5 volts and V negative was 5.01 volts, you would get 5 minus 5.01 minus 0.01 minus 0.01 times 200,000 minus 15. So all I need to know, and how can you forget this? You can't. If the positive is bigger than the negative, I get out plus 15. If the negative is bigger than the positive, I get out minus 15. So now, I say, look, V in positive is 2t minus 3. Okay? So V in positive is 2t minus 3. V in negative, as a function of t, I should have put function of t here, is 5t minus 10. Determine the output. It sounds daunting. It isn't. Here's the secret. Set the two equal. Set the two equal to each other. So we set them equal to each other, and you solve for t. Set them equal, set them equal, and t is 2 1/3 seconds. So now, what happens at 2 1/3 seconds? I change from either positive or minus to the other one. Now, which is which? Do I start out positive? Do I start out negative? How do you determine that? Exactly. Good. Plug in t equals 0. So what do I get? At t equals 0, this becomes minus 3, right? This is at t equals 0, right? This is minus 3. What's the value here? Minus 10. So V positive is a larger number than V negative. Minus 3 is greater than minus 10. So what do? We start out at plus 15. And what happens at 2 1/3 seconds? We go down to minus 15. So there, you already got Friday's lecture. on the integrator and the comparator, at least part of it. How did we do? Magdalena.
Comparator output if VP is equal to VN.
Right, this is a great question. If VP is equal to VN, turns out that a person in probability would say that's impossible because they have to be equal out to an infinite number of decimal places. An engineer would say, oh, come on, please. So what happens is we would say it's undefined. So here, this is T, and what was our number here? Let's say this is 2 1/3, right? Now, where does it start? This is V out. It starts out at plus 15, Magdalena? Right? So we start out at 15, and then it eventually goes to minus 15. What happens here is this. Okay? So if they're both exactly equal, the best answer we could give, it's undefined. But that's not going to happen. Not exactly equal anyway. And in reality, this is not a perfect straight line. You know, it's going to go down like this and like this. You know, so, but strictly speaking, to answer your question, undefined. It is switching from one to the other. All right, good. Here they come. Anything more that you might not like than short answer discussion questions or even shorter answer single word questions? All right. But let's see, I told you a lot of this was coming, right? Short answer questions. Now, really, you should look at the exam and not the solutions. You should be able to answer all of these, okay, without even looking at the answers. Okay. The input resistance, infinite. I remember sitting down and saying, I'm going to ask every question I can think of. All right? So the input resistance of an ideal amplifier, infinite. The output, 0. Now look, I told you this. I told you this in the lecture. Why do we love diff amps? Because it doesn't amplify common mode signals, and the number one common mode signal is noise.
So if you just said doesn't amplify noise, would you get?
Fine. An alternate answer. We are in sync tonight. A differential amplifier does not amplify noise. You got it? You got it. I know you got it. All right. Now let's just keep going. The value of the common mode rejection ratio, infinite. All right? That's the good gain divided by the bad gain, taking the log multiplied by 20. I want that number to be big. Now, come on. I'm not even going to show you the answer yet. You know this. You better know this. I said it 2 or 3 times in class. What is the cause of frequency? Look at the hand shoots up. It's like in Jeopardy. I didn't even get the answer out. He's going to phrase it as a question. What is the answer to what causes frequency distortion?
When it's nonlinear, in phase, something in phase.
You're giving me the right answer to a different question. Now, this happens so much on my exams. You gave me a perfect answer. What causes phase distortion? When the phase angle change is not linear with respect to frequency. See, I asked the wrong question, Professor Miles. See, this is on me, okay? I asked the wrong question. Let me tell you what I think is the quote-unquote right answer. What causes frequency distortion? The gain. Gain is not constant for all frequencies. The gain varies with frequency. Excellent. My good man, thank you. You got a good sense of humor. I love it. Are we okay? Okay, that's frequency. All right, now I'm up to F. By the way, I think I went for a record here. We're up to F. Wait to see what letter we get to. Okay. You are given a non-inverting 741 op amp, where this is the input. What's the output? Gain is 6.4 dB. All right? Now, the gain is 6.4 dB. First thing, convert the gain to non-dB. This was like the example we did in the class. I just changed the numbers. Convert the gain to non-dB. I know you can't read it. It's 2.09. That's the gain. So what's the output voltage? 0.7 times 2.09. Now, what else changes? Not the frequency, the phase. So if you look up the formula in the formula sheet, this is the formula we had on Friday, minus the arctan of F over FC. But I don't tell you FC. How'd you get FC? Exactly the gain bandwidth product. And what's the gain bandwidth product for 741 op amp? It's a millionaire. 1 million. Okay? So we say excellent. So now, just like we did in class, gain bandwidth product is a million. We solve, we get F sub C is this number here. Thus, and I know, I'm sorry, it's running off. It's right around minus 2.4 degrees. You'll see it in my PDF file. Now, last thing, the phase change is minus 2.4 degrees. So that means 0.7 times the gain times cosine 2 pi ft. Some people put minus 2.4 here. Broke our hearts. That's a phase change. I know. Can you believe this? I heard, no, exactly. That's what we were doing. It's 19.7 minus 2.4. We're almost done, kind of. We're doing good. G. Consider the drawing shown below. Ooh. There are 2 amplifiers in it and 2 segments of cable. The gain of amplifier 1 is 7 dB, and the gain of amplifier 2 is 9. The length of the first cable is 10 kilometers. The length of the second cable is 20 kilometers. The cable loses 0.4 dB per kilometer. Determine the total voltage gain in the system. Now you might say this is a made-up problem. It's not. If any of you have Comcast or exactly, these are. This is how they design what we call cable networks. Comcast, Altice, whatever they are now. This is how they have to design it. When do I put the amplifiers? So we say, what do I know? dBs add. All right? So what's the total gain? 7 plus 9, 16. Now, cables, the loss, 10 and 20 is 30 kilometers. 0.4 dB times 30. Is that 12? Just make sure that's minus. It's a loss. All right? So what we have is 16, the 9 and the 7, minus 30 times 0.4. And we get 4 dB, positive. So that's the total gain. We're good? We're ripping through these. All right. It's only one more page after this. A low-pass filter, here we go. I'm not going to show you the answer. Low-pass filter has a slope of minus 54 dB per octave. What's its order? Yes! Bingo! Ding, 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 ding. You got it, because each order is minus 6 dB. Very good. What filter type has a more linear variation? Let me pick someone at random here. My good man. What filter type has a more linear variation of phase angle with frequency than any other type we studied?
Oh yeah, it's the Butterworth one.
Well, it was the other B. That's right. See, I thought you would know this because you are a phase guy. But that's okay. It's Bessel. I'm sorry. I didn't mean to. That's okay. We're good. We're still good? We're still colleagues? All right, good. All right. All right. So we get Bessel. Look at this. I'm up to I. At this point, I was on a roll. Could I make it up to Z? I don't know. Okay. Filter type, sharp change. And ripple in the passband only. Chebyshev. Maximally flat. There you go. 2 last questions.
Well, that was just me not to include the fourth one. Not to include the fourth filter?
Oh, I didn't think that was mean. Should I? Oh, is that mean? I didn't mean it to be mean. Is that?
It's another 3/4 there, though. I mean, if you know it.
So.
Unless you get them all wrong.
So.
1 in 4 shots. It's still 1 in 4.
Now, what I often do is I might ask you the same one and it's the same answer both times.
That I would like, which is different wording.
All right. I didn't mean to, I didn't think leaving out the fourth was a bad thing. Now you got me thinking. I don't mean to be that way. As we discussed in class, the most common source of systematic error is? Right, calibration. Human error I probably would accept. What's the most common source of random error? And here's the formula sheet. I enjoyed tonight. Thank you. And we're getting out of here before it snows. Andrew and all your colleagues at SITTV, thank you. Good night, everyone. I hope it was worth your while. Was it okay? Yes. Thanks, everybody. You're great. You're great.